Here we present the formulas for the best fit parameters beta 0 and beta 1. Finding the best fit parameters by minimization of the error is equivalent to taking the derivative of the sum of the squared residuals and setting it to 0. You then solve the resulting equations for beta 0 and beta 1. Now we don't go through all the algebra steps here, and you can certainly find the derivation in most of the standard textbooks. The regression coefficients are often expressed in terms of the mean-centered variables. The formulas are then a little simplified if we subtract the mean from x and y first. We then have the coefficients s, xx, and s, xy, from which we can calculate beta 1 as the ratio of these two coefficients and beta 0 as the mean of y minus beta 1 times the mean of x. We can then write our linear regression model in terms of the best fit coefficients beta 0 and beta 1. This model can be used to compute regression predictions for new values of x, but be careful with extrapolation. The model is only valid for values of x inside the range of the original data. A regression analysis is designed to describe the relationship between two or more variables. What we want to do is to understand how to build the linear model. We want to learn how to make predictions, and we also want to test the statistical significance of the results. For example, a real estate agent may wish to predict a house price from various attributes of the house, for example, the size of the house or the number of rooms, etc., and perhaps also given some information about other typical houses in the area. Or we may wish to predict per capita cigarette consumption in a country based on various population statistics, such as income level or age of the population. We express these relationships in the form of a model connecting the response or the dependent variable and one or more explanatory or predictor variables. In the case of cigarette consumption, the response variable is the cigarette consumption measured by the number of packs of cigarettes sold in a given country on a per capita basis in a given year. The explanatory or predictor variables are then the various socioeconomic or demographic variables like age, education, income, etc. So we're going to look at how to build the regression model and how to find the best fit parameters using ordinary least squares. Having constructed the model, we want to know if the model is significant. So how confident can we be that there is a linear relationship in the data? And for this we need to examine measures of goodness of fit. For illustration purposes, we take here a bike sharing dataset. Here we've collected the number of bike rentals in a city and the average temperature on that day. There clearly is some relationship between the number of bikes rented and the temperature. On warmer days, it seems that more bikes are rented. How do we build a simple linear regression model for this data? We would like to use this model to tell us a little bit more detail about the relationship between the temperature and the number of bike rentals. Of course, Weka can do ordinary least squares linear regression. You can see from the screenshot here where to find the function which achieves this. You'll do some of these examples also in the next tutorial session. And so by applying the linear regression function, Weka helpfully tells us this easily interpreted form of the regression model. So it gives us a relationship between the output variable y and the input variable x. We can also see a lot of other information that Weka tells us, and we'll discuss some of the details of this. For example, the correlation coefficient and various error metrics. So this tells us the quality or how good we expect our fit to be. Now these terms will crop up over and over again in the lecture, so it's worth just defining them here in one slide. The independent variables, or the input, we often denote as x. The dependent variables, or the output, are usually denoted by y. For any one point, we have an input value xi and an observed value yi. So again, the index I is telling us the predicted value at that particular point. The parameters we'll call beta. In the case of simple linear regression, we're dealing with two parameters, beta 0, which is the intercept, So that tells us the value on the y-axis when x is 0, and the slope of the best fit curve, which is beta 1. The error epsilon I is the difference between our predicted value and the actual value of the data at that point. And again, it's common using these terms to represent the predicted value of y, or a given value of y, with a little hat. So you see there the hat over yi for the predicted value of y. Here we're showing the formal expression of the simple linear regression model, where we're showing the dependence of y, the dependent variable, on the input variable x. The parameters of the model are given by beta, beta 0, and beta 1. The way we interpret beta 0 is that it's the average value of the dependent variable y when x is 0. Beta 1 tells us the estimated change in the average value of y if we make it a unit change in x. So let's start with a first attempt at solving the simple linear regression problem. We want to estimate the parameters beta 0 and beta 1. These parameters are the ones which minimize the error in our model. The process for minimizing the errors could start like this. We could draw a line, any line, through the data. We would then compute the difference between the predicted values and the actual values. These are called the residuals. The goal is then to adjust the slope of the line so that the sum of the residuals above the line is the same as the sum of the residuals below the line. This is equivalent to minimizing the sum of the squared error, and this is the ordinary least squares minimization procedure. Here we present the formulas for the best fit parameters beta 0 and beta 1. Finding the best fit parameters by minimization of the error is equivalent to taking the derivative of the sum of the squared residuals and setting it to 0. You then solve the resulting equations for beta 0 and beta 1. Now we don't go through all the algebra steps here, and you can certainly find the derivation in most of the standard textbooks. The regression coefficients are often expressed in terms of the mean-centered variables. The formulas are then a little simplified if we subtract the mean from x and y first. We then have the coefficients s, xx, and s, xy, from which we can calculate beta 1 as the ratio of these two coefficients and beta 0 as the mean of y minus beta 1 times the mean of x. We can then write our linear regression model in terms of the best fit coefficients beta 0 and beta 1. This model can be used to compute regression predictions for new values of x, but be careful with extrapolation. The model is only valid for values of x inside the range of the original data. For the purposes of calculation, the mean-centered variables seem to involve a lot more work. So instead, I show here the best fit parameters beta 0 and beta 1 expressed in terms of the raw variables x and y. Once we have found beta 1, then the formula for beta 0 is the same as before. We show an example on the right-hand side of the slide, computing beta 1 and beta 0 from a table of data and applying the resulting regression model to predict a value for a particular x. Let's consider the sources of errors which arise from building the regression model. We can think of the error in the model being composed of an explained part and an unexplained part. These quantities can be expressed in terms of the sums of squares as SSOR, which is the variation in y which is explained by the regression line, and SSE, which is the variation in y that is left unexplained. The sum of SSOR and SSE is the overall variability in y, or SST. If the model is a perfect fit, then we would expect SSE to be 0, and in which case SST is equal to SSOR. So we have seen how to find the best fit line by using least squares to minimize the residual errors, but we can draw a straight line through any data set. What we would like to know is how good is our model, and we would like a measure which quantifies exactly how good it is. The general approach for testing how good our model is can be summarized with this p-value testing approach. We start by computing a test statistic on the sample data that tells us something about the hypothesis under consideration. We then take this statistic that we've computed and we convert it to a p-value by comparing its value to the distribution of the test statistic under the null hypothesis. We then want to decide whether we should reject or not the null hypothesis based on the p-value. And in general, if p is less than some threshold, then we reject the null hypothesis at that threshold level. The actual p-value depends on the problem, but usually we're looking at p-values of about 0.05 or 0.01. The appropriate null hypothesis for linear regression is then that there is no relationship between the variables x and y. This hypothesis, or the null hypothesis, is expressed as beta 1 equals 0. The alternative hypothesis is then that beta 1 is not equal to 0. The appropriate test for significance in this case is a two-tailed t-test, and we construct it as usual. You are provided here with the expression for the standard error of the variable beta 1, which, as you can see, is given in terms of the SSE, the sum of the squared errors, and the standard deviation of x. So we can quantify this relationship with the R squared, which is also called the correlation, or the coefficient of determination. And this measures the explanatory power of our model. Formally, it's the fraction of the total variation which is explained by the regression model. We can write it as the ratio of SSR to SST. And because of the relationship between SSR, SSE, and SST, we can also write it as 1 minus the ratio of SSE to SST. Again, it's worth noting that the correlation coefficient R squared does not tell us if x is the cause of changes in y. It's not about causation, it's only about correlation. As an example, we'd like to apply a t-test to a data set about car sales. In this data set, we have the sale price that was given at auction and the mileage on the odometer of the cars that were for sale. The best fit linear model is shown below. We would like to fit the linear model and then determine, using a t-test, how closely our best fit model fits the data. Using the values quoted here for the sum of the squared errors, the standard deviation of x, and the value for beta 1, we can compute the t-statistic, which comes out to be minus 16.657. How do we check if this is significant? Well, we can accept the null hypothesis with 95% confidence if t is between the quoted values of t, 1.976 and minus 1.976. These are the appropriate values of t for p equals 0.05 and the number of data points in our data set. Since the computed value of t is well outside of this range, we can reject the null hypothesis. Rejecting the null hypothesis in this case means concluding that there is a statistically significant relationship between the price that the car sells at auction and the mileage on the car. And of course, this negative relationship is clearly evident from the plot. In our discussion of the linear regression model, the dependent variable x and the response variable y have both been continuous numeric features. But there are many cases where the response variable is in fact categorical. An example would be a medical case where we've measured the age, gender, and cholesterol level of a set of patients, and whether or not they have heart disease. The response in this case, y, is a binary feature, yes or no, do they have heart disease or not. For a new patient, we would then record their age, gender, and cholesterol level, which would be a continuous feature. We want to predict the likelihood that they have heart disease from this data. The previous methods will not work well in this case for a number of reasons. the linear regression model has trouble extrapolating outside the variable range, and we also can't easily map the predictions of the model to categorical values. Now we know some better functions to achieve this smooth boundary. The most common one is the logistic function. It's shown here on the slide. The logistic function has a nice property of smoothly interpolating between the limits of 0 and 1. And it has a nice smooth S-shape which is controlled by the parameters beta 0 and beta 1. It's worth familiarizing or refamiliarizing yourself with the logistic regression curve. The parameter beta 0 is responsible for shifting the curve to the left or to the right, whereas the parameter beta 1 controls how steep the S-shaped curve is. Now we can rearrange the logistic formula to show that the log of the ratio of p to 1 minus p is given by the combination of parameters beta 0 plus beta 1 times x. In logistic regression problems, it's common to deal with the odds ratio. This is the ratio of the probability, or the odds of one outcome, to the probability of the other outcome. When the odds ratio is greater than 1, this describes a positive relationship between the variables. In the case of our tumor dataset, this would imply that an increase in tumor size implies the odds of a malignancy increases. When the odds ratio is less than 1, this describes a negative relationship. For example, as the tumor size decreases, the odds of malignancy decreases. How do we find the best fit parameters for a logistic regression model? In the case of simple linear regression, we could use ordinary least squares to derive closed form expressions for the best fit parameters beta 0 and beta 1. In logistic regression, there's no such closed form solution. Given independent observations or examples y, we could write a likelihood function for the probability of one outcome given the data. We could then try to find the parameter values which maximize the likelihood. But again, the algebra here becomes a little messy and there's no closed form solution, so we need another approach. The next few slides show how to apply the logistic regression model to our tumor diagnosis dataset using Weka. After running the logistic regression model in Weka, we find the best fit parameters below, and I've plotted this model in red for our tumor dataset. You can see how to make predictions for the probability that a tumor is malignant or benign for a given tumor radius. There are 2 points shown on the graph. The supervised learning problem can be represented in a very abstract and general way by the diagram on this slide. The general procedure we're describing is to start with some training data. Using this training data, we want to build a learning algorithm, and then we form a hypothesis about this data using the learning algorithm. The end result of all of this is that given a new input example, which we haven't seen before, we can feed it through our hypothesis function, and it will return a predicted value. Now we've already seen this procedure at work in classification problems and the regression models that have been shown previously. Some examples of the hypothesis functions that we've seen are the simple linear regression model, the logistic regression model. Our approach to learning models in general can be conceptually represented as a series of 3 steps. We start by choosing the function of a set of hypotheses which we wish to learn. This step is about representing the data in a formal way that the learning algorithm can handle. We then make a guess or a prediction from our model. And having made the guess, we need some way to quantify how good the guess is. We call this function the loss function, and it's at the heart of the evaluation step. The loss function is usually written as the squared error of the prediction minus the actual value. The final step is then to optimize the loss function over our training data. Optimization in this context is the process of finding the set of parameters beta which minimize the difference between our predictions and the data, or minimize the loss function. In the case of linear regression, we've seen how to do this exactly. But at least for logistic regression, we can't do it exactly. And this is in fact true in general. So we need to look at some other techniques for optimizing our loss function. The algorithm that we will use to do this minimization is known as gradient descent, and it's a perfect fit for solving this kind of problem. Gradient descent is an algorithm which is designed to find the local minimum of a function and has been adapted to work with a variety of functions in an iterative way. It doesn't need to know any details about the function we are minimizing, and it can also do this process very efficiently and at scale, so it's suitable for quite large data sets. Now, the simplest way to locate the local minimum of any function is to follow it in the downhill direction. This is equivalent to allowing a ball to roll down a hill. It will eventually come to rest at the lowest point. The key thing here is that we need to be able to choose the direction to move in. This direction should be downhill, and we can find this direction by computing the gradient of the function at each step. Once we know the gradient at any point on the function, we can take a small step in the opposite direction. That would be the downhill direction. Then we make the step and evaluate the gradient again. Eventually, we'll hit the bottom of the function, and the steps will no longer make any significant changes in the loss function. And then we can stop the procedure. Now, the gradient descent algorithm is not guaranteed to find the precise local minimum, but it should get very close to it. To formalize the procedure of gradient descent, we write the update step like this. At each step of the iteration, the new value of our parameter, beta, is given by the old value plus some delta, or step. The direction of the step is given by the derivative of the loss function, so we want to move to smaller deviations. And the size of the step is determined by the parameter alpha. Generally, we start the process with an initial guess for the parameters beta. It turns out not to matter much where we start. Now, for any general loss function, to compute the gradient descent, we need to be able to evaluate the derivative of the loss function with respect to the parameters beta. This is fairly straightforward to do in the case of simple linear regression. We show here on the slides the update steps for the parameters beta 0 and beta 1. Now, the update steps for beta 0 and beta 1 are very similar, except you'll notice in beta 1, because it has this dependence on the variable x, so in the hypothesis function we have beta 1 times the variable x. We end up with a factor of x in the sum. As an exercise, you could go through a similar process for finding the update steps for logistic regression, and you may find the formula for the derivative of the logistic function to be useful here. How do we choose the learning rate alpha? Well, alpha determines the size of the adjustment that's made to the weights at each step in the gradient descent algorithm. There are in fact many strategies for choosing the best value of alpha. A typical range for this starting value of alpha is something in the range of 0.0001 to somewhere about 10. If alpha is too large, then the steps that we make in the gradient descent iterations are too large, and this means that the gradient descent algorithm can miss the local minimum, or it finds it very difficult to get close to it. However, if we set alpha to be too small, then the steps don't progress quickly enough towards the local minimum. We may never reach that point. So occasionally there's a process of trial and error involved in setting alpha, and there are other procedures for setting it which depend on the rate of change of the loss function as well. But for this course, we'll start with an initial guess for alpha, in that range. We'll use a constant value of alpha throughout the whole gradient descent algorithm. On this slide, we show the basic pseudocode for the gradient descent algorithm. The inputs to this algorithm are usually the learning rate parameter alpha and the maximum number of iterations, Kmax. The first step in the procedure is to set the parameters beta 0 and beta 1 to some initial values. You could choose random points in parameter space, or you could set them both to be 0, which again is commonly done. You see then in the iteration step we've got this sum of the loss function, which is the hypothesis function minus the data y. Now when we compute this sum, it's important that we use the current values for the parameters beta 0 and beta 1. Again, we're using these to compute the update, or the new value for beta 0 and beta 1. So it's important that we only do the updates after we've computed the values of the sum. In this case, it's helpful to work through a few steps or a few iterations of the gradient descent algorithm. And you can do this with a reduced sample of the bike rental dataset, which you'll find on Moodle. As we perform each iteration of the gradient descent, it's useful to consider the cost function, which is basically the difference between our current best fit hypothesis, using the current values of the parameters, and the data. This is essentially a snapshot of the function that we're trying to minimize. So again, you can see on the plot on the right, typical progression for the cost function as the number of iterations increases. So the cost function initially decreases very rapidly, and then after a certain number of iterations, which may be a few hundred, it seems to stop changing. At this point, it's generally a good idea to stop your gradient descent algorithm because you're making no further improvements in your best fit parameters. On this slide, we show some of the steps in the progress of the gradient descent algorithm. This again is for our bike rental dataset, and the best fit model found by ordinary least squares is shown in the black line. The red line represents the current state of the parameters as found by gradient descent. In this case, we've set the initial values of the parameters beta 0 and beta 1 to both be 0. So you can see there the red line, the top left plot, has an intercept of y equals 0, and it's a straight line along the x-axis, because beta 1 is 0. After a few iterations, in this case 50, we see that the y-intercept beta 0 has increased to almost 2, and beta 1 is clearly non-zero as well. It has some positive slope. After a few thousand iterations, in this case about 9,000 or 10,000 iterations, we see that gradient descent is starting to approach the best fit by ordinary least squares model. So it's common to stop gradient descent after a certain number of iterations have been performed. It's also common to set a threshold function for the stopping procedure. So in this case, we might decide that when the loss function changes below some threshold value, then at that point, it's not worth continuing on the gradient descent, and so we can stop. There are a few details we need to consider about how to perform the updates in gradient descent. So far, we've computed the total loss function as the average loss for each training example. So you can see in the formula that the loss is summed over the difference between the predicted result and the actual value for every single example. And it's only after all of these residuals have been computed that we perform the actual update. This is called batch gradient descent. You can immediately see the problems with batch gradient descent when you have large data. The updates are going to be extremely slow because we have to perform a lot of work before we can make the updates. An alternative to batch gradient descent is stochastic gradient descent. With this method, instead of taking all the training examples and updating them in one step, we take one example at a time and we perform the update directly. You can see in the examples at the bottom of the slide that batch gradient descent tends to move very steadily downhill towards the minimum. But stochastic gradient descent is going to move in random directions. It's only on average that stochastic gradient descent moves downhill. The surprising thing about stochastic gradient descent is that it can make extremely good progress with a very small number of training examples. Ultimately, it should converge to the result that batch gradient descent does. In practice, we find that updating one example at a time doesn't allow us to take full benefit from parallelization. So instead, we take batches or groups of training examples together, update this little batch in a group, and then repeat for a new batch. This is called mini-batch gradient descent. The mini-batch size is a parameter that we have to choose somewhat carefully. If this value is too small, we get no benefit from parallelization, but if it's too large, we're back to the default of batch gradient descent. You can use Weka to learn a simple linear regression model and also a gradient descent for the bike rental data. So what I've shown here is a comparison between the linear model that Weka finds for simple linear regression and the one that it finds by gradient descent with 500 iterations. And you can see that the values of the parameters beta 0 and beta 1 are not quite the same for gradient descent, but they're getting pretty close. If we increase the number of iterations in this case for gradient descent, we may find that the parameters beta 0 and beta 1 approach the ordinary least squares model. And so in summary, in this lecture, we've looked at two regression models: simple linear regression for numerical features, and logistic regression, which is more suitable for categorical features. We've also looked at a general approach to finding the best fit parameters for these models, called gradient descent. This is an iterative algorithm suitable for finding the minimum of a cost function. Our regression models can be cast in the form of a loss function, and we can learn the best fit parameters using gradient descent. You will find that the gradient descent algorithm crops up in many other areas of machine learning.